last but not least, we might wonder, okay, what is the equation for the arc length of a polar curve? Because, essentially we have three different types of coordinate systems, and this is not an extensive list of all the possible, but the most commonly used: parametric, rectangular, and polar. It's nice to know how to do calculus in any of those systems. And one other thing you might be wondering is, okay, Professor, what if I'm trying to do volumes of revolution or a surface area or all those things that we did with rectangular functions? Basically, we're not going to worry about doing those sorts of shapes. We're not going to worry about doing those in polar and parametric form, just because I think this is an extensive enough look at how to do calculus in these coordinate systems. And again, in Calc 3, you're going to learn a lot of other techniques of working with volume and surface area and so forth, without even needing to use these formulas, doing it basically using double and triple integrals. But anyways, let's go ahead and finish kind of with arc length, since we did arc length in both rectangular and parametric. It turns out it's quite simple to do in polar form as well. And we'll do a quick example, say finding the arc length of a cardioid. So to begin with, well, again, we could always think of a polar equation in parametric conversion. We talked about this when it comes to the slope. Same exact method we did for finding the slope of a polar equation, which is if our equation of our polar equation is r as a function of theta, whatever it might be, solve for r, then we can use the conversion relationship, because x is always equal to r cosine theta and y is always equal to r times the sine of theta. So if we plug that in, we would get this parametric equation. Anyways, this would describe a polar equation in parametric form always. And since we already know the parametric equation of an arc length, we can simply plug that stuff in. But what I wanted to show you is there's quite a vast simplification of the formula, which is where the formula for polar arc length comes from. And it turns out you're just taking the square root of r squared plus the derivative squared, something you may not I probably would not have guessed it's quite that simple, but it is. So let's get into it by subbing it in. So basically, we're gonna have the integral across our parameter, whatever values of theta we need to do for our polar curve. And if we're looking at dx d theta, that would just be the derivative of the x component with respect to theta, which again, we're gonna need to use the product rule to do. We already did this before, but it would be first d second. Derivative of cosine is negative sine, plus second d first, so f prime theta cosine theta. And that would all be squared, and all of this is within a gigantic square root. I probably should have written this more on the left, but whatever. Now dy d theta would be very similar by product rule, first d second plus second d first. So first d second would be f of theta times derivative of sine is cosine, plus second d first is sine times f prime. And all of, whoops, I wrote that in a square root. I meant to write that in a square, because again, we're going to have dx dt squared plus dy dt squared, all of that within a square root. And if we integrate that with respect to theta, this will give us the arc length of the curve. And now we're trying to change this to polar form instead. And actually, let me go ahead and write this as using Leibniz notation instead. Sorry to change it up on you guys, but f of theta, that's just the same as r, and f prime of theta is just dr d theta. And this now will match up with what we have below. So we got negative r sine theta plus dr d theta cosine theta, and then again, f theta is equal to r, and f prime theta is equal to dr d theta. Whoops, get rid of that too. Sorry, I did not plan this out very well. No matter. So we, basically to square all this, we're going to need to FOIL. So let's go ahead and just give ourselves even a little bit more room to explore all of what's happening in this massive thing. But, so to square it, we're going to need to square this. We're going to have r squared sine squared theta. Then the inner product multiplied by 2. So this would be minus 2r dr d theta sine theta cosine theta. And then this squared would be dr d theta squared cosine squared theta. And you might have a hard time believing that all this crap is gonna, sorry, it's not crap, you know what I mean? All this stuff is gonna magically turn into this. But it does, so let's just see why. And then in the second one, again, we're gonna need to FOIL this out. So the first thing will be squared, r cosine squared theta. And then it'll be plus the inner product times 2. So plus twice r dr d theta, cosine theta, sine theta. And then plus the last thing squared, which would be plus sine squared theta dr d theta squared. So a lot of algebra, and what we end up having is a bunch of stuff. One thing that you might be noticing is that the inner products for these two things are exactly the same but opposite. So let me go ahead and underline that. This and this are exactly the same thing when we multiply. Essentially, when we're multiplying the terms within dx d theta and dy d theta. But and of course, since one is positive, one is negative, those will cancel each other out and leave us with 0 there. So that's quite a bit simpler. And what you'll also notice is that we have common terms that involve these two terms involve r squared. So if I collect these together and rewrite them, so I'll just go ahead and highlight this one and this one as terms that involve r squared. And then let's go ahead and use another color to highlight. These ones both involve dr d theta squared. And actually, what's interesting is both of them, one of them involves cosine squared and one involves sine squared. And since cosine squared plus sine squared equal 1, that's why all of this simplifies so drastically. So let's just reorganize and factor here. But let's put the two green things together and factor out r squared. So we'd have r squared sine squared theta plus cosine squared theta. And then in the second part, we have a common factor of dr d theta squared. So if we factor that out, what we'd be left with is cosine squared plus sine squared theta. And all of that is with respect to theta, because those two red things canceled each other out. And well, in both cases, happenstance, well, it's not a coincidence, but they both happen to be a sum of both sine squared and cosine squared. And as we know, those are both 1. We get cosine squared plus cosine squared is 1. Cosine squared plus sine squared also 1. So both of those go to 1. And we end up with simply r squared plus dr d theta squared, all within a square root, and this gives us the arc length of a polar curve. So, again, another formula. At the end of the day, it turns out being quite simple. Let's practice using it, and it will wrap up our series on polar and parametric calculus. So let's say we wanted to find the length of a cardioid. Again, it's kind of like, we don't call it the circumference because circumference is that of a circle, but it's kind of the same idea. What's the length of the perimeter? Or if you were to walk all the way around this curve, how far would we have traveled? So again, first thing we need to know is, well, what is dr d theta? Just the derivative of it. Well, derivative of 3 is 0, and derivative of cosine is negative sine. And I think we did this one earlier when we were working with the cardioid with derivatives. But if I just square those things and put them in within a square root, the arc length of the curve should be, well, r squared, so 3 plus 3 cosine theta quantity squared, plus dr d theta squared negative 3 sine theta squared. And all of these integrals are starting to look very similar to one another as we continue to do these examples. And if I'm trying to find the length of the whole cardioid, I would need to go all the way, around, but one full period or cycle of that cardioid would be, again, 0 to 360. And now simplifying all of this, actually, I believe this is just the same integral that we just solved, but let's go ahead and just double check. So if we multiply all of this out, well, again, to square this, we need to FOIL it. So I'd have 9 plus twice the inner product. So the inner product here is 9 cosine, so it would be plus 18 cosine theta, and then plus the second term squared, which would be plus 9 cosine squared theta. And if I were to FOIL this one, I don't need to FOIL, it's only one term. Squaring that would just be plus 9 sine squared theta. And what you'll notice is that sine squared plus cosine squared is 1. Well, since it's 9, I could factor the 9, but this would make a total of 9. 9 plus 9 is 18. It's actually not quite the same integral as the one we just did over here for the cycloid, but is almost the same. We end up with the square root of 18 plus 18 cosine theta with respect to theta. And similarly, 18 is a common factor, so we could factor that out. And that would be 1 plus cosine theta. And again, the tactic that will work for this type of integral, which again is a new tactic we did not see when we were in chapter 7, but involves using the power reducing identities in reverse to take 1 plus cosine. In the last integral we used this one, but now what we have is 1 plus cosine, and we know that 1 plus cosine is equal to twice cosine squared. And again, the angle will half, because here it's double, here it's half of the other side. So ultimately, this will leave us with 18 times 2. Dang it, I already forgot. This one, let me leave it up there. 1 plus cosine will turn into cosine squared. And again, the angle will be cut in half with respect to theta. And notice what we end up getting is, well, again, the square root of a square. That's why that was so helpful. And 18 times 2 is, of course, 36. So that also is perfectly square. So we'd end up with 6 cosine theta over 2, technically absolute value with respect to theta. And we could throw this in our calculator to finish the integral. Obviously, we could have done that from the very beginning, but let's go ahead and finish it off since we're already on it. But let's just go ahead and say if we were to do u substitution where u is theta over 2, then du would be d theta over 2. And so we'd have twice du. Basically, we would have a factor of 2 in this. So this would be equal to 12 times the integral from 0 to 2 pi. Well, and actually our boundaries of our integral will change if I'm doing a sub. Because if theta is 0, then u will be 0. And if theta is 2 pi, then u will be pi. So integrating from 0 to pi of cosine u du. Now the next question that arises, okay, what's the absolute value, or what's the integral of the absolute value of cosine? We've never done this sort of example. Though, if you remember, for those of you who had me for Calc 1, we did actually examine the integral of an absolute value because technically it is a piecewise function, and that's kind of the crux of the matter here. Now, of course, you could do it in a calculator, but since we've already taken so much time to try to solve this, let's go ahead and consider how we would approach this. But if we think about the integral of cosine from 0 to pi, cosine, by the time we get to, 2 pi completes one cycle, but pi, it's gone down to the negative side. And at pi over 2, it's at its halfway point. Well, it's a quarter of the way through one period, but it's the point where it has an x-intercept. But essentially, the integral of cosine, if we integrate from 0 to pi, it's going to give us 0 if we don't have an absolute value. So the absolute value of cosine is almost exactly the same curve. Whoops, let me erase. I erased this a little bit too far, and I'll go ahead and draw it, say, in green instead. But it will, be the same up until pi over 2, and since it's an absolute value, it will be changed to a positive value. And we're going to have a similar looking graph. But essentially, the area under the curve should be the same over here. So another way that we could do this if we wanted to not worry about the absolute value and use symmetry is just integrate it from pi, integrate it up from 0 to pi over 2, and then double the answer. Because as we know, a cosine wave has symmetry, is always symmetric. So let's go ahead and just do that instead. But another way of doing this is if you're like, well, how would I integrate this? Well, we could think about it as a piecewise function where it's just equal to a normal cosine function when we're going from goes from 0 to pi over 2. But since the absolute value would change the sign, it would be equal to negative cosine u for pi, as we're going from pi over 2 to pi. And so I could change it to the form of a piecewise function. And in order to integrate a piecewise function, we would need to basically integrate each of these separately. But it's going to fix the problem that if you don't have the absolute value, it's going to give you an answer of 0. If you, because the integral of absolute value cosine is not just sine, or it's not just absolute value sine either. Well, actually, that's a point for another video. But let's go ahead and just use symmetry. But of course, my point was we could separate this into two separate functions and integrate them over the specific sections the same, but it's gonna, you know, at the end of the day, we're going to have a symmetric answer. So we would have, well, 12 multiplied by, basically what I'm going to do is I'm going to change it from 0 to pi over 2, integrating only halfway, finding this area, and then I'm going to double it because that will be equal. The area underneath cosine here is equal to that there, and the absolute value, as I explained earlier. But what we're going to end up with is 24 multiplied by the integral of cosine u du from 0 to pi over 2, and the integral of cosine is, of course, sine. So we're going to have 24 times the sine of u from pi over 2 to 0. And sine of pi over 2 is 1, and sine of 0 is 0. So I'm going to end up with 24. And anyways, long story short, we found the length of the cardioid. I can clearly see I did not give us enough room to fully do this question on our page, which I do apologize for. But it's a fairly tricky example to fully flesh it out. And, you know, at the end of the day, if you ever are stuck with an integral, and most of the time when you're dealing with arc lengths, because they are such complex, you know, integrals to solve, we often just use a calculator, Maxima, computer algebra system to find the answer. But I wanted to show you guys some examples of doing it by hand, you know, where on an exam, you know, what are some potential types of questions we could be faced with. But basically, the circumference of a cardioid is very, you know, is almost exactly the same as the arc length of a cycloid. There's a huge similarity in those structures. But, you know, what we end up with is a number that does not involve pi either, and exactly a value of 24 at the end of the day. So you can, again, this is another curve where you could look up the length of a cardioid, which just depends on, well, what's the value of its radius. Well, technically, if you're like 3 is not called its radius, but it's sort of like if you're thinking about this as the center, notice it's kind of like 3 away in both directions. I digress, but again, it's consistent and kind of an interesting answer. Anyways, that will wrap up our lecture series. Have an awesome break. When we come back, we will be starting chapter 11, and we'll do a little review as well for the upcoming exam.